Can everyone hear me okay? Yep. So, hey everyone. Thanks for inviting me to be here. First time at r2con, first time speaking. So thank you to everyone organizing the conference already. Even with the trainings, this has been awesome. So yeah, originally this was going to be like a 20-minute presentation. And with all of the movement and stuff, we're going to try and speak a little bit slower. I was trying desperately to get as much information in and speak really fast so I could tell you a lot of stuff. But now I can slow down and speak slowly. So yeah, today we're going to look at using R2 and R2 Frida to analyze some protected iOS apps. And I'm kind of speaking about a really narrow concept, not everything to do with protected iOS apps. I'm not really delving into obfuscation and things like that, but at least showing you something that is not new, but isn't really that well documented. And some people ask me this question a lot and, when they're looking at apps, so I figured it would be nice to share it with you. So the idea is basically, like me a few years ago, I don't know how to drink from the glass and use R2 and R2 Frida or hook Syscalls or anything like that. So I figured rather than just figure it out and keep it to myself now, maybe I can share some information and help you. So this is kind of like a little bit of a journey. So I'm just going to talk a little bit about how this was happening before with Substrate and ARM32 and how we were doing things in the past. And writing things down on pencil and paper and making mistakes with addresses and messing the application up. So yeah, basically like a journey from being a total idiot to slightly less of an idiot. So that's the idea, right? So yeah, mainly we're going to talk about 64-bit iOS, but as I said, there is a little bit towards the beginning where we talk about ARM32. And predominantly, other than maybe like 2 slides, I'm going to talk about Syscalls. So is everyone aware of how Syscalls work? Anyone who's not familiar? Okay, good. So yeah, I mean, on iOS, they're no different than other platforms. But what's happening is a lot of applications will use inline assembly to invoke system calls to circumvent the standard library, so that when we're using Frida to try and intercept various library calls, then we don't get to see what the app's doing. So furthermore, we're going to talk a little bit about automation, right? So using R2 pipe and maybe even some R2 Frida plugins towards the end, so that you can do this stuff faster without actually having to spend a lot of time manually. The other thing is probably most of this applies to Android, but the caveat is I don't do anything with Android. So the native layer, like there's a lot of similarities. But yeah, I mean, Gio's speaking later. He does way more Android than I am, so go see him. He's more of an expert. So some of the reason why we're doing this stuff, obviously, like all of you, we do this for fun, or sometimes we're paid, or sometimes you read Giovanni's blog and get jealous and want to learn like him. So go see his talk. And yeah, basically just finding this stuff takes way too long, and bypassing it can take even longer, and it's just a pain in the ass. So if we can use some automation, then we can actually get to the more interesting stuff quicker. So yeah, other than Syscalls, some examples of things that are typically happening in apps. Usually they try and stop us from instrumenting the app in a number of different ways. So looking for things on the file system is the obvious one. So on jailbroken devices or devices where we have things like Frida present or Substrate present, there's residual artifacts that are there on the file system that they can pick up. And obviously they're doing this with common APIs like stat, open, and access, and so on. You can also look for these things in memory. So really common, again, like loop over all of the libraries that are loaded in the process space, look for the name Frida, really basic check, but many people do it. And then, depending on which platform and how you're using Frida, it's not always going to appear there. So there are some tricks to identify the Frida paths in the memory regions without actually using the DYLD image iterations. So the other thing you can do is you can be looking for artifacts or evidence of Frida across memory, so strings or some kind of fingerprinting of Frida or Substrate that you might be looking for. So again, this is really common in various applications. And then there's this thing which many people in the room probably are familiar with, and many people might not be. So on macOS and iOS, you have this flag or environment variable where you can use it to preload libraries. So it's called DYLD insert libraries. And in the linker, they have some code that says if you have a segment and section with the name __ restrict, then you ignore the environment variable. So I'll show you an example of this on Mac in a second. But yeah, the first time I was looking at this was even pre-Frida, and even in my constructor and my hooks, the basic log statements weren't even there, and I was pulling my hair out. Like, I mean, this should work. It does nothing complicated, but my libraries weren't even being injected. So, yeah, I lost way too much time on that one. But it's really simple now that you read about it. So, if you want to do it, you can compile with Clang or GCC or whatever and add the sections. They don't need to contain anything. They can be empty. But in this case, using R2, we just print the bytes of the section, and you can see it says, hello, r2con2019. And then the last thing is, which again is very common, many of the products out there, the RAS products and stuff, they're looking for identification of tampering to memory. So looking for any kind of alterations to the code. So checksumming of the code, sometimes running in other threads. They look for evidence of repackaging in case maybe we're not even using jailbroken devices. And then looking for certain trampolines inside target functions, so that can be in the standard library or even in their own functions as well. So as an example of the restrict section, if you look at various applications on both iOS and Mac, you'll find this. And so here we have iTunes on the Mac, and if we print out with R2, with Rabin to get all of the sections, we can see here we have restrict, and if we try and use Frida with the process, it tells us that we can't. And if you go ahead and remove that section, then you can attach. So yeah, really basic once you know about it, but yeah, if you don't know about it, it can cause a lot of pain. So I'm going to try not to offend Ole here. I'm going to try and talk a little bit about how this works, but not specific to Frida, but also with Substrate. So the basic idea, again, many people in the room will be familiar, but under regular circumstances, your application calls functionality in the standard library, let's say access. The function runs, does a wiggle, and then execution comes back, right? So it's fairly simple. So if we use some kind of hooking tool that uses trampolines, then what happens is the diagram might look a little bit weird, but we have some kind of replacement of some instructions in the target function, which is going to hijack execution and run some replacement code. So when the application now calls the function in the standard library, execution's passed to us, and then optionally we can either we can replace the functionality and never call the original, or we might call the original if we don't want to try and re-implement whatever it was that they did, and then finally execution goes back to the app. So really like hand-wavy sort of basic example of how this stuff works. But why is that interesting? Well, because many applications actually detect this. So as an example, with R2 Frida, you can ignore the first command now. You don't actually need to import the information anymore. I think Pancake last week made some changes to automatically do this, which is awesome. So if we print out 2 instructions at the address of open, you can see we have some ARM64, store a pair of registers, and some move instruction. And if you use the \di1 command in R2 Frida, you replace the return value of the function. So in this case, we want to alter the function to return 1, and it uses interceptor underneath. And now if we print out the first 2 instructions, we can see these have changed, right? So in the red circle, you can see some opcodes, and if this has been detected even Substrate and for a while, and as I say, many products do this. And here even from a white paper in 2016 from Vincent Tan, he shows like a really basic example of identification of these opcodes. So you pass a function pointer, check for the opcodes, and if you find them, then someone's tampering with it. So again, very common practice now. So much of libsystem is exposed via system calls, obviously. So typical interaction as a developer, you make a function call in the standard library, then standard library invokes a system call. And on iOS, there's in excess of 400. I think, I'm not a Windows guy, but I was reading there's like in excess of 1,000. So different platforms obviously operate in different ways. But here the numbers exceed, I think, even 500, but there are around, I think, 400 unique. But you can print these pretty easily. So there's tools out there like Joker, which is another open source where you can print out the system call table if you pass it in iOS firmware. And thanks to Mr. Machete, who's somewhere here, I think, R2 can also do this. So now if you give R2 a decompressed kernel image, you can go ahead and analyze it as well and do many more things, but you can get the system call table or the trap table as well. So R2 also has some of this built in via some internal commands. So you can use like the AS commands for accessing information about the system calls. So you can do like both lookups by name and the inverse by number. So you can, for example, look up ptrace or read or socket or whatever it is that you're looking for. Or if you want you know, a list of these, you can use ESIL as well. So how this works on iOS. On iOS, the instruction for supervisor calls is svc ox80 for system calls, and on Android, I think it's svc 0. And it follows the standard like calling convention for functions. So x0 through x7 is going to hold your first arguments, and then thereafter the arguments will be on the stack. But what we really care about is that the system call number that's being used is going to be in the x16 register. And again, I'm not an Android guy, so it could be wrong, but I think it's x12 or something like that. So basically, if we have this call here to socket, what would happen, you know, if we wanted to call this, we would have our constants, they can go in the registers, and we can look up with R2 the system call number for socket, which in this case in hexadecimal is 61. And then if we go ahead and call the instruction, then we can, you know, we can make that happen. So this is the way it works, and knowing that, we can start to build some tooling to find out what's happening and identify what the applications are checking for. And the trouble was, in the beginning, the way I was doing this was analyzing the application in like Hopper and you know, going through, finding these things by searching for the mnemonics one by one and writing down the address in ARM32 and putting it on some paper and then putting it into some substrate code, and you had to compile it, and then the application crashed because you made an error with one of the addresses, or one of the addresses that was actually ptrace, you put it in the socket you know, array, so you hooked it like a socket call. So this was a real nightmare, but it was all I knew, and I was still learning this stuff, so it was, yeah, really painful. So back in the beginning, I had some really basic Hopper scripts to just go through and find the svc ox80s, print out the addresses, but this was like 5 years ago, and even Frida has been around longer, but I wasn't really aware or using it. But the trouble is, this is just, I have no patience for this. Now that I know like the better way of doing it, I'm like, I don't even like to admit I was doing it this way. So the trouble is, like, in that context, I was printing out like a list of addresses with no information. I have no idea what the system calls were. It was just an arbitrary list of offsets. So I was going again by each one in tools like Hopper or IDA and just looking for move instructions to see the value going in. And then obviously, as apps are obfuscated, you can't really see that too easily. So you know, this was a bit of a problem. But then we figured, like, yeah, we could use Substrate to hook these, right? So anyone who's written Substrate hooks, I figured, like, yeah, we can just go ahead and do this. But it doesn't really support out-of-the-box hooking of like just an offset or an instruction. You have to have a valid function at that address. So some people that I was working with, they came up with a sort of hacky, well, a very hacky workaround. But basically just using the MS hook function of Substrate, but then changing some instructions to make it work. And so this is, again, ARM32, but not ARM64. So this was, again, allowed us to now hook all of those and replace the functionality, so we could now see everything they were doing with access and socket and so on. And then we ended up having like huge sets of hooks for all of the standard library, all of the things that we know from jailbreak detections or anti-tampering. And then we had like these arrays, again, which I was populating manually for ptrace, close, read. And then we were looping over those and calling, patching all of them one by one. So this was fine. Like when applications had like, 10 to 50 syscalls, like going through manually doing it one by one is like only a small effort, but still too much effort. But apps now have like thousands. Like so many have like several hundred or even in excess of 2,000, depending on what kind of product is in use or how paranoid they are. And so I figured like, okay, if I could do this at runtime, even in Substrate, if I could figure out the system call number at runtime, then I don't need to manually figure out which one's which. I don't need to put them into different arrays and do all this clumsy stuff. I could get it at runtime. Trouble is, if you remember what happens when we replace a function with interceptor, the register that holds the system call number is used during that process. So the system call number is actually no longer there. So we have to do it in a couple of different ways. So there's a number of ways you can get around this. And it's the same for Substrate and Frida on iOS. I think on Android it's actually okay. So I started getting all crazy again late at night, thinking, yeah, I'll write some Hopper script that generates a debugger script that set, breakpoints and prints out the value at runtime, and then I can put it into Frida script. And eventually I ended up just changing some Frida source, so don't use this because it broke a bunch of stuff. It was accepted and then immediately discarded because my ideas are crazy. So basically I just changed all of the usage of x16 to x18 since it's meant to be like an unused register, but it is used. It turns out. So we have some other ideas. We were speaking just a second ago with Ulla and Mr. Machete about other ideas we could maybe do, which we'll, I guess, talk about after the conference. But yeah, there are other ways of doing it. You can use Stalker, for example, as we'll see. But then the other problem is, like, I don't have time for all of this. Like, I don't want to install an app, run it, trace it at runtime, and even some of the system calls might not even run. So I figured, like, okay, let's go back to the drawing board, do this statically. And a colleague at the time, Edu, he was at r2con, and he came back and he was doing the CTF internally, and I'd never used R2 up until just after last r2con. So I was like, okay, this looks like way more extensible and pluggable for what I want to do. So I figured that if I can scan the app statically and find out most of the stuff, then that would be ideal. So yeah, I'm still learning. So again, many people in the room use R2 a lot more than I do. But yeah, you can find the system calls in a binary with /as. It will tell you which system call it is, which is handy. And we can also use the /at command to give some instruction types and get information there as well. But if you look at the counts, there is some variance, right? So we can see there's a little bit of context when we use /as, but when we use /at, we get more, but we don't obviously know which system call it is. The other thing is I don't really want to analyze the whole binary, because in large obfuscated binaries, it takes too long. And the last thing is, towards the end, when we do this at runtime, we don't really need to look by mnemonics. We can look for the opcodes, which, as you can see with the timing, is significantly faster, right? So this was just in a small application, but in bigger applications, it can take like 15, 20 minutes when it's searching. So obviously doing it in a smaller factor of rounds is much more appealing. So I started to build this tooling based on R2pipe, which hasn't seen the light of day yet because it's really messy and has missing features. But basically, you can give it an iOS app. It'll go through, look at the main binary, figure out all of the linked libraries, and basically recursively scan them all, identify where all these things are used. And for some stupid reason, I decided it would be a great idea to create an XML output instead of JSON. So I'll show you a quick example. I have a crack me. We scan it with the tool very fast. We're also doing some signature matching for various products. And then we get like some information. So here we can see there's ptrace exit access. And the tool even, you can feed that back in and it automatically hooks them all in Frida. All the system calls get hooked and it traces everything that's happening. So that was like the first approach that I went down. Works fine, but again, it could be better. In obfuscated apps, sometimes I wasn't able to see the system call number, especially because I hadn't done the analysis. Because again, I want to do it as fast as possible. So I figured like maybe I'll use ESIL, and Conduit was saying already, don't use iocache equals true, so I'm going to have to change this. So yeah, I'm still learning. But yeah, basically we can use ESIL. We jump back probably more than is necessary, but just seek back and then set up the emulation and go ahead and emulate until that point. And you can see here before when we get the system call number, it's nothing. And then afterwards, we can see it's sysctl, which is for anti-debugging, or for many things, but probably for anti-debugging. So we built this in, and it looks something like this, really bad Python code. It's a trend when you look at my code. And basically, it works. It runs everything. All of my hacky print statements are now commented out, so nice. And the result is we get something like this. So different app, not sysctl, but we can now see there was a call to the system call for getPID, and we annotated to say that we emulated it with ESIL. So if we wanted to extend this and use Unicorn or something different, then we can do that as well. So yeah, moving one step better, we can do this with R2 Frida, and we can also use R2 pipe with R2 Frida, which if you were in the training the other day, you would find out from the last part of the presentation. So again, you can ignore the /i asterisk, it's no longer needed. But here we basically want to search for the main binary because it's a crackme that I wrote for the training, so I know it's not in any other libraries. So with /dm, we can get the maps for the current loaded process, and I just want to filter by the executable region. And then we can seek to that location and use /e/, which will set all of the search parameters in the environment variables of R2 to the current image that we're currently seek to. So here when we do /e/, you can see all of the search parameters are the same boundaries of that code block. And now if we want, we can go ahead and use //x to search for hex pairs. And we can use the assembler functionalities of R2 to actually even get us the opcodes for the SVC instruction. So, I mean, not that it's hard to remember the opcodes, but you know, if like me, you're doing a lot of stuff and you want to search for different things, you can just chain the commands, really nice. And we search only in that region, and we find 63 hits. So in challenge 1 of the crackme, spoilers in case you want to do it at home, but challenge 1 is using the standard library, and challenge 2 is similar, but with system calls. So here we have 63 matches. So with that, we can use other commands. So for example, in R2Frida, you can use /DTR, which will trace registers at a particular given address. So like other functionality of R2, you can use the iterators. So we can say, let's trace the current address with X0 register to print it out at all of the hits, right? So for each of those, we want to find out what's in X0. And the reason we chose X0 in this case is because those system calls are access and I think lstat, which the X0 is the file path. So when we do that, what happens in R2Frida is we can see the path that's being searched for. So they're looking for Cydia in the crackme. I say they, me. I'm looking for Cydia, and I found it. You know, if this was a real app, we could see the paths that they're being searched for. Although searching like this and tracing on all the hits isn't really going to work because they're going to be different system calls. But we can, again, we'll get to being more creative than that. So the other thing is you can do this with Stalker. So without having to make changes to Frida, you can use Stalker because Stalker is less invasive. So here what I did was I dumped all the system calls into a dictionary in the JavaScript for, I think, iOS 12. But they don't really change all that often. But once I have them there, I can trace functionality. And it's very slow, but it works. So I'm tracing all instructions, and if I see SVC, then and it's also part of the main app. So you might want to do it for other libraries as well, but for here I'm just limiting it to the main app. If I see an SVC instruction, then I call out to some other functionality. So over on the right-hand side, you can see what I'm doing. My code basically gets the value of the program counter. Just in case I want to print that out to say where it is. You could also work out the address, the static address, if you want to feed this into R2 scripts offline to add comments or annotations or anything like that as well, which I'm currently adding now. But also we can parse the register value of x16, and we can look it up in the dictionary. So now we can create some switch cases or anything to handle access, ptrace, socket, or anything else, right? So now we can be more creative. So in Frida itself, not in R2Frida, but in Frida, here's an example of that working. So on the crackme, if you use the Stalker-based approach, we can see all of the access calls, and we can see all of the file paths that are being searched for. And furthermore, if we want to bypass those checks, we can just use the Frida APIs to replace the string with a file path that doesn't exist. With the caveat that obviously you could have red herrings and stuff. So if you replace everything, then again, they might still pick you up. But you can see here, we have the flag for the second part of the crackme. So basically the next steps were, okay, we can do this in Stalker, we can script this stuff, but you know, I was looking in the last few weeks to see that you can actually write plugins for R2 So I figured, okay, like if I can write a plugin that will do this easily, I don't have to worry about chaining the different commands, or if I want to replace certain system calls, I can put that all into a plugin and make it like really easy to use. So commands will probably change. Again, it's really messed up code right now, but you can use like \st, F to find them all. You can stock all of them with S to print out what all the system calls are, and with T, that's where I'm starting to build the logic in to allow you to put like blacklists of files that you want to replace. So we can actually start to do more. So again, like just like in the previous example, we're now calling it from within the plugin in R2 with \sts, and you see the output from the script. So it's really easy, actually. I don't really like JavaScript, sorry. So I have a buddy who's like really hardcore JavaScript. I'm like, dude, what the fuck is a promise? So I'm trying to call two R2 host commands, and it was just hanging. And he's like, yeah, dude, you have to chain the promises. I'm like, okay, sorry. So basically, you can register command handlers for different commands. In this case, I just have one, and I have arguments that I pass to it. And the code looked way nicer than this, but Stalker relies on duct tape, or at least currently. There's some problems with V8 in R2 and V8 is the default in R2 So if we want to use Stalker, we need to turn that off, and then I had to like find some website that was going to convert my syntax to something old school. So it's still not too bad, but yeah, it was looking better. So yeah, here we can use the commands that we know from R2, like PA that we were using in the previous example. So we can say PA with the mnemonics, and we can get the opcodes. And then we can go through, look for executable code regions. We can go ahead and search for the system calls and populate them in some JavaScript objects. And the result of that is now, like we did before, we have a plugin where we can find and bypass all of these. Again, really basic functionality for now, but maybe we can make it better going forward. The other thing that I said I would mention, Pancake worked on this, I think, a month ago or something. But there's also the option to inject code using Frida as well. So you can use this code here to inject system calls and invoke the functionality if you want to. So you can also do that. So what's next? Keep writing bad code and hope it works. But yeah, we can get very far using R2pipe. One of the limitations I found so far with writing an R2 Frida plugin is I wanted to just use the commands that I was using before, like the \/x to search for the bytes. And you can do it with the Frida. I could do it with Frida, but I figured if that logic's already built in, I could just reuse it. I had to use both Frida code as well as running R2 commands, which is probably the neat way of doing it. But with R2pipe, you can obviously make use of the R2 Frida commands as well. So it's quite a bit more extensible for me, and also I don't have to worry too much about the JavaScript side because I can use Python. So the next steps for me is to try and identify different detections, different products. There's a tool out there, Edu, and some others work on it called APK ID. So I figured like there's no iOS equivalent. Maybe it would be good to work on something like that. But then also for these things to create some kind of mappings to help you work out offline. So as I say, maybe adding some comments in R2 offline to show you what the system call number was, what the arguments were, maybe if you can't find it through ESIL. And also creating some graphs that will help you figure out where things are. So when you're looking at really complicated apps, often you're working through the backtraces, and then you hook those things, and then you see what they call. And again, we can automate a lot of this stuff, so that's the plan. So yeah, ideally I want to have two options, either to scan and get as much information offline as I can, but if I have to run the app, which is becoming more common, then I can run the app and I can trace everything at runtime. The other thing is to show the example of how this will work at some point. As I say, I need to make it neater, and there's a few things missing. But also, I think Gio is going to talk a lot about Dwarf, which is like a debugger built on top of Frida with many other capabilities, and he's also now making it extensible to write agents. And again, it should be pretty easy to add something like this cross-platform for Dwarf, although he might even have that already. So. Yeah, that's it for what's next. I have screenshots. I can show you a demo if we have time. I guess we definitely have time. So let me go ahead and do that. So how do I do this without taking a video of myself? Yeah. Okay. So let's go here. And yeah, let's go, shall we? Just make sure I have the thing in the... Okay. So yeah, basically I can show you the plugin. We can go here. Let's go. Yeah. So if we take a look at the code, let's look at the new code, I guess. Let's do this. So again, we have the dictionary. The plan is we can use that from the AS command, so we don't actually need to do that. But again, I'm lazy, haven't got around to it. So yeah, we have some commands here to handle the different arguments that we as users are going to want to use, so whether we're finding them, tracing them, or doing other things. We are trying to add some support for Android, but as I say, I'm not an Android person, so I'm not a cyborg. So here we have the code which calls the r2 commands to get the opcodes like we showed. And down here, if we want to stalk, we call the stalk Syscalls function. And if I jump to this, I can show you what that looks like. Okay, here. So again, right now I'm just creating a POC, so it's limited to the app region, but super simple to fix. And when you're finding them, it creates a mapping for all of the libraries in memory and shows you which ones belong to which. So we can easily leverage that going forward. And yeah, if we find one, then we're just going to go ahead and print it out. But as I say, maybe we can import that information into R2 offline, so we can create some scripts to create comments and flags and other things that will help us when we're analyzing this statically. So really basic stuff, but let's go ahead and run it. So let's just make sure that. Let's go spawn. USB. Let's just see if I can find. Okay. So I think, if I remember correctly. So what happens in the Crack Me, if you want to play along at home, if you have an iPhone device, when we spawn with Frida or R2 Frida, obviously the application is running, but in like 15 seconds, the OS is going to kill us because the application hasn't been resumed, and it says, yeah, time's out. So we can resume it, and what's going to happen is the application is going to detect us and self-destruct. Again, fairly common when you're analyzing apps like this. But what we can do, we can import challenge 1, and we can go ahead and resume. So now we see some code. Wait. Now the application obviously doesn't crash. So challenge 1 is fairly easy. It's nice trying to use a laptop when it's slanted away from you. So yeah, basic example, we have a blacklist based on the tracing that we did of some files. And with Frida, we're hooking access, and we're also hooking LStat. It's not really that portable because instead of using args, I'm using x0 just because I'm lazy or because I want to look cool. I don't know. So yeah, challenge 1 is really easy, and now obviously if we go to challenge 2, it's going to crash again, right? So we go to challenge 2, it gives us like a 2-second timer, and yeah, application's dead, right? So let's go ahead and restart, and let's go for challenge 1 again, and let's resume. So we beat challenge 1. And now if we want to, what we can do, I've put together some commands already. So if we wanted to automate this, we can either batch up some commands and pass them in with -i, and it will run all of those R2 commands. Or we could put it into R2pipe, or we could put it into a plugin. So here, all of the commands I showed earlier, we have them batched up to automatically bypass challenge 2. So I'll show you this one first. So let's go ahead and actually let me change something real quick. Pancake's going to hate me, but I'm going to use Nano. So let's go ahead and do find R2. So I just want to import challenge 1. Okay, so let's go ahead and run that, and we can say -i and do find R2. So let's go ahead and run the app, spawn it again. Now we can see we have the blessing of Clippy, right? It doesn't work if you don't use Clippy. So here we bypass challenge 1, and then we need to resume the app. And now, obviously, we can see some other stuff. Okay. And what's going to happen is if we go to challenge 2, we should beat the challenge. So here you can see it says it's going to self-destruct, but it doesn't. And if I search for x0:, we can see the flag, but also we can tab through. There's free detection, there's jailbreak detection, there's various other stuff. So we can do all of this from within the batch script. But also, if we want to, if I tab back out, and actually let me restart just for cleanliness. So let's say challenge 1 again, and let's resume. And then if we want, we can go ES5. Yeah. So let's go ahead and import the plugin, and now we can go ahead and use the commands. And so we can do like \stf. It will go through and, as I say, recursively look for everything, but you don't really want everything necessarily. And again, it's hacky, so there's some JavaScript objects because I don't know what I'm doing. So here, if we want to go ahead and, for example, trace, we can run Stalker now, and we'll go ahead and run the challenge. You'll see it's a little bit slower with Stalker, but let's give it a try. And yeah, again, this is just a crack me, so you know, using this in real apps is going to take some time to get it working, but let's go ahead and give this some seconds. Yeah, I know why it's not working. So again, I was saying Stalker has some issues right now with V8, and if we load up with R2, yeah, I'm gonna have to kill this, haven't I? Okay, looks like it's fine. Okay, so if you want, you can do like this, and you can see the runtime is V8 and FreeDet defaults to duct tape. So we have some problems here. So yeah, we'll let it do its thing. It's going to destroy itself. So if we want to go ahead and do that, then I think I remember the command. Yeah. So let's go ahead and do this. And yeah, we can just go here. So if we set this environment variable now to, let's say, disable V8 to 1, and we're going to go ahead and spawn the application again, we still have the commands being passed in, but we'll go ahead and take them out since we're going to do it with the plugin. So here we need to go ahead and import challenge 1 again. We can resume, click OK. And now if we want to, we can import the plugin. And we have the commands again, so just same as before, we can still search. That's not the problem. It's when we want to go ahead and run Stalker. So now you see it doesn't hang on the first thread. We have some more information, so let's go ahead and go to challenge 2. Okay, so now we can see that some access calls were called. And let's go try one more time. and let's do challenge 1 again. So this is just to trace the system calls that are running. But if we want to implement the bypasses we did a second ago, we can use the final command. So let's go ahead and run syscall tracer. So in this case, I think we ran STS, right? Otherwise, my code broke. Yeah, okay, it's fine. So this time we run st with t to say we actually want to trace to do more stuff than just trace. As you can see, the syntax doesn't really make sense yet, but we'll figure it out. So, yeah. Okay, still died. Bad demo. But yeah, basically, the idea is we can go ahead and build in blacklists and for common things. These exist on many platforms. So if you go looking around white papers in GitHub, you'll find lots of examples of anti-jailbreaking, anti-tampering, and we can go ahead and start populating some kind of knowledge base of this stuff, and then pass it in here. So yeah, I mean, demo's not exactly working. I mean, I was working on this stuff right up until the end of last week. So, but yeah, you get the idea. So the idea is we need a little bit of time to make this work better on iOS, and then we need some Android people to come help. So yeah, I guess that's everything. Yeah. So. Any questions?
Well, thank you for your presentation, and I want to tell you that I will be doing the Android part. So I already tested, and it was more or less working, but I think I will port it in like 1 week or so no worries.
Nice. Thank you.
No question?
Thank you. Thank you. Yeah, it's an interesting journey. Thank you for sharing. Only one question. During your journey, why you did not consider LLDB scripting?
Yeah, I mean, I did. I was doing a lot of stuff in LLDB, and even as you say, like halfway through, I figured like let's just create some LLDB scripts to do this. And even some colleagues I'm working with, where I show them this stuff, they are doing the same stuff in LLDB. Just preference. I'm not opposed to using a debugger, but yeah, I mean, I'd rather do stuff which is more extensible and I can change things on the fly. And yeah, for me, I prefer it. But yeah, no real reason. I guess you could do all of this the same way, but for me, just prefer using tools like Frida and r2frida. So yeah.
Thank you.
More questions? Okay, thanks.